Hello and welcome to the first video of the FP1 chapter, Proof. GCSE review question on the screen to get us going. Pause the video now if you've got time, give this a go. Here we've got the question, prove that this expression is an even number for all positive integer values of n. So if you want to prove something, there are different ways to go about it depending on what you're trying to prove. In this case we're trying to prove it's an even number. So what we want to end up with is 2 times something that we know is an integer, because 2 times an integer will always be an even number. So we're just going to take this expression, expand it out, and see what we get. That gives us a 4n squared plus 4n plus 1 minus 2n minus 1. Collecting like terms, we end up with 2n squared plus n. And we know that any positive integer value of n will make this expression here an integer. And the 2 in front, 2 times that integer, will always be an even number. So we have proven that this expression will always give you an even number if n is a positive integer value. What we're doing here in this chapter is proof by induction, and every video here is the same proof style, by induction each time. However, it's quite useful to see examples in the different types. This is series, divisibility results, recurrence relations, and matrices. But before we get to proving results about series, let's talk about what this method actually is. It's a very powerful tool, and it is done in 4 steps. In terms of exams, you need to show all 4 steps to get full marks. And I'm going to start with step 2 of the proof, just because it's a bit more intuitive to explain it this way. We'll come back to step 1 in a moment. So we're going to start with an assumption. And that assumption, very simply, is going to be the thing you're trying to prove. I'm going to call it here the general statement. So the generalized statement, the thing you're trying to prove, we're going to assume it is true for n equals some integer k. Now this is obviously not the proof part of the proof, because we're assuming something that may or may not be true. But on the back of that, we are going to do an inductive step, and we're going to prove that if this is true for n equals k, then it must be true for n equals k plus 1, the next integer. So let me say that again. The proof here, the inductive step, we're going to prove that if the general statement is true for, say, n equals 7, if it's true for n equals 7, then it must be true for n equals 8. And this is the idea of induction, is that if you can prove it's true for the next integer, then you've proven it for all other integers after. Because if I prove that if it's true for n equals 7, it must be true for n equals 8, then obviously if it's true for n equals 8, it must be true for n equals 9. If it's true for n equals 9, it must be true for n equals 10. If it must be true for the next one, then it will be true for all of the ones after the one I've shown is true. This is often compared to dominoes. If you set up all of your dominoes in a row, you don't need to push each one over, you just push one of them over and all of the rest of them follow. That's kind of what we're doing here. But the problem at the moment is that we don't know that this is true for n equals k. And we've got this big if statement. So that's where we go back to step 1. This is called the basis step. And that is to prove that it's true for n equals 1. If we've proved it must be true for the next integer, and you've proved it's true for n equals 1, this is like pushing over the first domino. If it's true for n equals 1, which we can show just by putting that into the statement and showing it's true, then it must be true for n equals 2. If it's true for n equals 2, it must be true for n equals 3, and you've proved it for every integer after the one that you've shown is true. The final step is just a very simple conclusion. where you write out that it must be true for all positive integers n, because you've proved it's true for n equals 1, and you've proved it's true for the next integer. So that's the idea. Let me emphasize again, though, that you should show all of these clearly in an exam to get full marks. Particularly the idea that without this basis step, without the proof it's true for n equals 1, you have not proved it to be true. And without the proof that it's true for the next integer, you have not proved that it's true. These two here together make a proof. In terms of the exam, making it all nice and formal, you should also include your assumption and your conclusion. But it's these two here particularly. You must not leave out this one. Otherwise you have not finished your proof. And the rest of this video, and the following 3 videos, there are very few notes. There's only one more little note to make, and it's all examples. But I would recommend that you watch the 3 different videos following this one, because we're going to do series specifically in this video, and it kind of gets a bit samey. Once you know what you're doing, you can just follow through. But if you apply this to divisibility rules or matrices, it just feels slightly different. So I would recommend, although we're using the same process in each of these 4 videos, I would recommend going through a few examples from each of them. So here's the first one. Prove by induction that for all positive integers n, the sum of the series 2r minus 1 from 1 to n is n squared. So I've got the steps up here, and I'm going to try and keep the color coordinated. I'll do my basis in purple here. So I need to prove, first of all, that this is true when n equals 1. So the left-hand side of my statement, the sum, is the sum from r is equal to 1 up to n, which is 1. So that's just the first term of 2r minus 1. The first term of this series is 2 times 1, that's 2, minus 1, that's 1. Right-hand side, we need to make sure that this agrees. N squared, if n is equal to 1, is just 1 squared, is 1, yes. So we've shown, therefore, true for n equals 1. And that's the basis. But now we need to prove it's true for the next integer. So I'm going to assume, and the thing I'm going to assume is this general statement I'm trying to prove where n is equal to k. So I'm going to assume that the sum from r is equal to 1 to k of 2r minus 1 is equal to k squared. And I'm going to use that in my proof. So the next step, the inductive step, the important step where most of your work is going to be, is I need to prove the sum from r is equal to 1 to k plus 1, the next one, of this same series, 2r minus 1. I need to prove that that is this thing with a k plus 1. So instead of k squared, what I should end up with is k plus 1 all squared. If that's the case, then I've proved it. How do I do that? Well, with series, it's quite straightforward. You do more or less the same thing each time. You're going to split this series into 1 to k, so just one below this, and then add that on separately outside of the series. Because obviously this series here we know is the first term plus the second term plus the third term all the way up to the kth term. This is first term plus second term all the way up to the kth term plus the k plus 1 term. So I'm just going to take that k plus 1 term off the end and add it manually, as it were. So I'm going to split this into r equals 1 to k of 2r minus 1, and then add on that k plus 1 term separately. And k plus 1 in this series, the series is 2r minus 1. That's 2 times k plus 1 minus 1. So I've just decomposed this slightly into 1 to k, and then the extra k plus 1 term to make it 1 to k plus 1. And the reason I do that is because of my assumption. I assumed I know what this is. I've assumed that this is equal to k squared. So using my assumption, I can write that as k squared. And that's why there's this if statement. If this is equal to k squared, then the thing that I'm going to prove will be true. So it's based on the fact that this is true. And that's why I need to show that it is true for at least one of these. And that's why I needed to do this. So if this is true, and we know it is true for n equals 1, so if this is true, I can do that, but I still need to add 2k plus 1 minus 1. Expand this out, and we get 2k plus 2 minus 1 plus 1. And this, of course, if you factorize it, k plus 1 all squared, which is in the format n squared, where n is equal to k plus 1. So I have proved this is equal to this, so this is true for n equals k plus 1 if true for n equals k, because we used that in this process. So this is true if this is true, and I have proved over here that it is true for n equals 1. Therefore it must be true for n equals 2. And it's true for n equals 2, therefore it must be true for n equals 3, and so on and so on. The idea of the dominoes falling there. Therefore, and this is saying this one and this one together must mean that it is true for all n natural numbers, which is what we want, all positive integers. So that's it. We're going to do a few more examples following more or less the same idea, and then the next video will be slightly different because it will be slightly different sorts of things that we're proving. In the previous chapter, we used two formulas that I didn't prove. I'm going to prove them now. The first one is the sum of the square numbers, then I'll do the cube numbers, and then we'll do a slightly more interesting question at the end of the video. Same thing, basis step first, n is equal to 1. We've got the left-hand side. The left-hand side here is the sum from r equals 1 to n, which is now 1, of r squared, so that's the first term, that's just 1 squared, which is 1. The right-hand side of the statement is 1 over 6 times n, which is 1, times n plus 1, that's 2, times 2n plus 1, that's a 3. 1 times 2 times 3 is 6, divided by 6 is 1. So it is true, the statement is true for n is equal to 1. Great. Now I'm going to assume it's true for n equals k. So the assumption is r is equal to 1 to k of r squared is equal to 1 over 6 times k plus 1 times 2k plus 1. And again, I'm going to use that assumption in the next step, which is the inductive step, proving that from 1 to k plus 1 of r squared is equal to this thing, where the n will be a k plus 1 instead of a k, as we had here. And to do that, I'm going to split it into the sum from 1 to k of r squared, plus the k plus 1 term, which is k plus 1 squared. Now I use my assumption that this thing here is equal to this thing, 1 over 6k, k plus 1, 2k plus 1, and adding k plus 1 squared. Now sometimes there's a certain amount of creativity as to how you actually make the thing that you've got using your assumption into the particular form of what you need with a k plus 1. It wasn't too bad in the previous example, it just kind of happened. Here I need to think a little bit more carefully how I get into this format, and in some questions like the last example, it takes a bit more thought again. So here what I'm going to do is factorize out k plus 1, and I'm going to pull a 1 over 6 out as well, which will leave us 6 here in this term. So 1 over 6 times k plus 1. There's two reasons I'm doing that. That's because the k plus 1 is a common factor. It's just going to make things a bit easier to get that out the way. but also the n here for n equals k plus 1, that is now correct. The little bit here, 1 over 6n, is in the correct format. So that's great. So let's see what I get left. I've got a k here, 2k plus 1 from this bit of the expression, and from this part of the expression I need a 6 because I took a 1 over 6 out where there wasn't one, and I've got a k plus 1 bracket left. So now I'm going to simplify this by putting it together and hopefully make it look like this where n equals k plus 1. That's going to give me 2k squared plus k plus 6k. Let me rewrite that as 7k straight away. Plus 6 times 1, 6. And that, if I can just squeeze it on the bottom here, factorizes into two brackets, 2k and a k. Then we must have a 3 here and a 2 here. Now that doesn't look like this. But don't worry, because what we need to do here is to pull a k plus 1 in little brackets for our n. So this k plus 2, if I make this a k plus 1 plus 1, that's this bracket here where n equals k plus 1. So I'm just going to manipulate how it looks to make it exactly what I need. So jumping up here, I've got 1 over 6, k plus 1, and then from the bracket on the end, I can write k plus 1 plus 1, and from the bracket in here, I can write 2k plus 2 plus 1. And hopefully you can see where I'm going here. If I factorize out the 2, this will be 2 brackets k plus 1 plus 1, which is 2n plus 1, where n equals k plus 1. And there we have finished our proof. K plus 1 here instead of n, k plus 1 here instead of n, k plus 1 here instead of n, and everything else matches this format. So I've done the inductive proof step, but I should still be really clear in my exam. Therefore, true for n equals k plus 1 if true for n equals k, because we used n equals k as an assumption. But we know it's true for n equals 1, therefore it must be true for all of the others. And there we go. Next example is fairly similar. If you don't really care too much about proving the r cubed one, skip over onto the final example, which is slightly different. But I said I would do this, so I'm going to go for it. We've got left-hand side, sum from 1 to 1 of r cubed is 1 cubed for the first term. Right-hand side, 1 over 4, 1 squared, 1 plus 1 is 2 squared, that's 4 divided by 4 is a 1. So it is true for n equals 1, yes. Now we're assuming that it's true for n equals k. And that would be 1 over 4 k squared, k plus 1 all squared. And what I'm trying to prove is that it's true for k plus 1. Now sometimes what I do is think about what that would look like if I actually had a k plus 1 in there. So let me say what it should end up as is k plus 1 squared, k plus 1 plus 1 squared. And what this does is help me to realize when I get to the end of my proof, I will probably have a k plus 2 in a bracket that I can split into k plus 1 plus 1. Here we go. So r is equal to 1 to k plus 1 of r cubed. Again, for series, it's fairly similar each time you do it. Split it from 1 to k, and then add on the k plus 1 term. Then add your assumption in, which in this case is 1 over 4 k squared, k plus 1 squared, plus the k plus 1 cubed term. And I'm going to do something very similar. It's quite similar to the previous example. I've got a k plus 1 squared here, k plus 1 squared here, 1 over 4, and I'll force a 1 over 4 out here to give me a 1 over 4 k plus 1 squared common factor, which matches this part here, where n is equal to k plus 1. And then I see what I get left. I've got k squared here, and 4 lots of k plus 1 here. But 1 over 4 k plus 1 squared times k squared plus 4k plus 4. And this is actually a slightly easier example because we can see that factorizes straight away into what we want, k plus 2 squared. And then just to really make it clear for the examiner, split that out into a k plus 1 plus 1 squared. Therefore, true for n equals k plus 1. If true for n equals k. And at the start we proved that it's true for n equals 1, therefore it must be true for all integers after that. And there we go. Final, slightly different, slightly more interesting example. Prove by induction that this is true. This is r times 2 to the power of r is equal to this expression. So do the same thing. Prove it's true when n equals 1. We've got the left-hand side. Sum from r is equal to 1 up to 1 of r times 2 to the r is equal to 1 times 2 to the 1, which is a 2. The right-hand side, 2 times 1 plus 1 minus 1, that's 0, times 2 to the 1, so all of that bit is 0. 1 plus 0 is 1, 2 times 1 is 2. So yes, it is true for n is equal to 1. Assume true for n is equal to k. So from r is equal to 1 up to k, r2 to the r, we're going to assume it's true. So we get 2 times 1 plus k minus 1 times 2 to the k. And this time, again, I'm just going to see what it should look like if I put k plus 1 into this. So I would have a 2 there, a 1 plus, and then here I would have k plus 1 minus 1. So that would simplify to a k. So I might end up with a k that I can change into k plus 1 minus 1. And then I'll have a 2 to the n, where n is k plus 1. So probably I'll end up with this, and then to make it really clear, I'll force this k to be a k plus 1 minus 1 to make it in this format. And that just helps me not to panic if it comes up like this and I think, oh no, I need a minus 1 in there. There is a minus 1, it's because the k also has a plus 1, where n is equal to k plus 1. So, proving this, r is equal to 1 to k plus 1 of r2 to the r is equal to the sum of r is equal to 1 to k of r2 to the r plus the k plus 1 term, so that's k plus 1 times 2 to the k plus 1. Using my assumption, I've got 2, 1 plus k minus 1, 2 to the k, plus the k plus 1 term. And in this case, I'm just going to expand everything out and hope that it kind of simplifies to something like this. Sometimes proofs are a little bit more, you've got to be a little bit more creative, which is why it's good to look at some of the other videos, even though it's the same process, because sometimes they're not as simple it just falls out when you simplify it. Whereas here, I think it will. We get a 2 plus 2 times this, and I'll expand this bracket as well, so that's 2 lots of k times 2 to the k, 2 lots of k times 2 to the k, and 2 lots of minus 2 to the k. So we've got minus 2 lots of 2 to the k. And then the other bracket, k lots of 2 to the k plus 1, and 1 times that, so that's just 2k plus 1. Now here you need to appreciate your indices work. I can add this 2 into this expression for 2 to the k, because that's 2 times 2 times 2 k lots, and then times another 2, so this is 2k plus 1. So let me rewrite that as k 2k plus 1. Same here, I can put this 2 into the 2 to the k part of the expression, and that is minus 2k plus 1. I can't do much here, and I can't do much here. But now that I've done that, I can see that this term and this term cancel out, and this term and this term are the same, so I'll add them together and we'll get a 2 there, but I won't put it into this expression. I won't make that a k plus 2. I'll leave that 2 out because I know I want to factorize the 2. So we've got 2 from the beginning plus 2 lots of k 2 to the k plus 1, and then factorizing that out, I get 1 plus k 2 to the k plus 1, which is where I might have panicked, because that doesn't look much like this, but I know that it is the same. I can just do a plus 1 minus 1 in there to force this into the correct format. There are lots of brackets there. Here we've got k plus 1 in place of n, k plus 1 minus 1, which is why it just simplified to a k, to make the n minus 1 in this bracket. And then we've got 2 to the k plus 1, a 1 in front and a 2 in front. So it is correct. So this is true for n equals k plus 1, if it's true for n equals k, and we've shown already it's true for n equals 1, therefore it must be true for all positive integers. And there we have it. That should be plenty for you to have a go at questions from exercise 8a about proving sums of series statements, and in the next video we'll look at divisibility rules. Maybe I'll see you there.